All right, hello and welcome. I'm here with our crystalline silicon solar cells lecture series, and today we're going to dive into our manufacturing part 1. So let's look over our outline. So today we'll touch on each of the physical aspects of a solar cell: the wafer, the emitter, the anti-reflective coating, the back surface field, the front contacts, and the losses, which is really going to be talking about how to balance all these things. There's key characteristics to each of the things we'll talk about today, and there's a way to balance them to get a great solar cell. So as you'll see here, there's 4 different types of solar cells. The 2 on the left are monocrystalline, the 2 on the right are polycrystalline, and we'll talk about that as we talk about the wafer. So the wafer absorbs light and generates electron-hole pairs. Just like we mentioned before, it's the opposite of a light bulb. So there's 4 major characteristics of a wafer. You have your crystallinity, which is either monocrystalline or multicrystalline, like we mentioned earlier, the doping level, the area, and the thickness. Those are your major metrics for a wafer. So typical wafers come P-type. They're either mono or multi, it depends on what you're looking for. And they have a resistivity of 0.1 to 10 ohms centimeter. And their area is 156 by 156 square. That's centimeters square, and they're about 180 microns thick. They're cleaned and textured, and you diffuse into them, and it's basically, the wafer is your blank canvas to build a solar cell. So let's look at our trade-offs. So what happens if we have a really thick wafer? Well, our absorption will go up because you have a really thick wafer, you have a good depth that you can absorb things, but your collection will start to go down because your excited electrons or holes have to travel a long way. So then let's look at a thin wafer, right? Now it's less distance, so you have lower recombination. The electron hole or holes don't have to travel as far, but just like before, your absorption goes down because you have less thick of a wafer. So if your wafer is only this thick and the light shines on it and it needs this much distance, or it travels this far into the wafer before it gets absorbed, you're going to miss that light. But usually, most likely it's absorbed at pretty low depth into a wafer. And then also another win is if it's really thin, you need less silicon, so it costs less. But that runs out eventually because when you get shorter than 180 microns, your wafers get really brittle, and then your yield will drop because they'll break much more often. So then we'll look into the doping. So there's 2 major types of doping, P-type and N-type. Right? One is doped with phosphorus, one is doped with boron. Generally, wafers come P-type because it's easier to make an N-type emitter. So it's easier to make a P-type bulk because it's already melted down, and you add in the appropriate chemicals to get P-type. But when you're making an emitter, it's a lot easier if you just diffuse phosphorus into it. So that's generally wafers come as P-type. And then we'll touch on the doping density when we talk about the emitter. And then lastly, the crystallinity. So remember, we have multi and mono. Multicrystalline is cheaper, but its recombination is much higher because it doesn't have a consistent crystalline structure. Multicrystalline's got all these crystalline structures kind of interacting. It provides a lot of recombination where I have one crystalline structure and then another crystalline structure, and there's a lot of recombination at the boundary. Whereas with monocrystalline, it's a consistent structure across the whole thing. There's no grain boundaries, or at least a lot less grain boundaries. But then it's more expensive. So now let's jump into the emitter. So the emitter is typically the N+ region, so it's N+ at the front of a solar cell. You diffuse phosphorus into a P-type wafer to get an N-type emitter. And why does the emitter exist? It separates the excited hole pairs. It's your junction. So the major characteristics are the doping profile and the sheet resistance. And most often an emitter is about 0.5 to 2 microns deep into the wafer. That's where your junction is. And then really to figure out how highly it's doped, you measure the sheet resistance, and usually that's about 45 to 200 ohms per square. So let's look into junction depth. So junction depth, if you look at the graph, is where your phosphorus and your boron concentration intersect. That's your junction. So if you look at this one, your phosphorus comes down, intersects with your boron, and at that point, that's your junction depth. So usually, most of the carriers are generated near the surface, so you want your junction close to the surface. But if the emitter is extremely thin, so if your junctions are really close to the surface, then your emitter will be very thin, your series resistance will go up. So you got to balance those two. What's my optimal junction depth where my series resistance is low, but also have my junction up where the carriers are being generated. And the other trade-off is your doping density, which is the same trade-off you have with your bulk, your P-type wafer that you get. So if you have a really high doping density, your VOC goes up, your open circuit voltage, which is what we want, right? We want a high VOC and a high short circuit current. And our contact resistance goes down, which is great, because we have a high doping density. The energy that it takes to jump from the emitter to the metal is less. And also, there's less dangling bonds in the metal contact, so it's more passivated. But if it's a very high doping density, your Auger recombination goes up and your Shockley-Reed-Hall combination goes up. Remember, if we have a really high doping density, we have a lot more electron or holes excited in the conduction band, and they'll interact, and sometimes they'll hit, and one will get heated up and the other one drops down. That likelihood goes up a lot more as there's more electrons available there. And then also Shockley-Reed-Hall obviously will go up because you have more discrete energy levels that come from doping, because doping is technically a defect. So now let's look into the anti-reflective coating. So the anti-reflective coating is exactly what it says. It's just an anti-reflective layer right at the front, because you don't want light to bounce off. You want light to go into the wafer. And basically, an anti-reflective coating is about 75 nanometers. You don't want it to be too thick either, because it will absorb some light. And it has an indice of refraction of somewhere from 2 to 2.6. And that's your anti-reflective coating. It isn't as difficult to balance this one. You want to get a good index of refraction, and you don't want to be too thick, is basically your variables there. And it's typically silicon nitride. The next thing is the back surface field. So that's your rear contact. So it's a sheet of aluminum on the very back of your wafer. Fortunately, when aluminum is fired into silicon, it creates a P plus layer, which is great because we want to draw the holes to the back and the electrons to the front. So aluminum is also not very complicated, not as delicate of a balancing act. You basically just slap aluminum on the back, screen printed or deposited, and run it through a belt furnace and fire the aluminum into the silicon. It's nice, and it's a little more simple. The next thing is the front contacts. Front contacts is a little bit more of a balancing act. They're typically made of silver paste, and they're on the front surface. There's usually 2 or 3 bus bars in the front. So bus bars are just thicker silver on the front, and fingers are just thinner silver on the front, and they're all connected. Usually what you're deciding, what you're really juggling is how many bus bars do I want, how many fingers do I want, how thick do I want those, how far apart do I want my fingers, and the thing you're juggling is your resistivity, your contact resistivity, and your series resistivity, and also your shading. Because if you have tons and tons of bus bars and tons of fingers, you'll have really low sheet resistance, but you'll shade a lot of your wafer. So typically you have 2 to 3 bus bars. Your finger width is about 90 to 100 microns, and they're about 2 to 4 millimeters apart. So like we mentioned before, if your distance between fingers is really wide, you're going to have a lot of shading, but very low, so very high. I'm saying this backwards. If your fingers are very far apart, you have very low shading and very high sheet resistance. Similarly, with finger width, if you have a really low width, you'll have very low shading, low metal area. But again, your series resistance will be very high. And then your contact resistance is more determined by the doping that your metal is sitting on. But you can run into some issues. Because there's silicon nitride on the front, remember that anti-reflective coating, the silver has to have this glassy layer in the paste, the glassy chemical added to the paste, to get through the silicon nitride. So sometimes that causes some issues. Hopefully it doesn't. If you fire appropriately, screen print appropriately, it'll etch through the silicon nitride and your silver will be right on the silicon. So that's it for that's it for today. That's our brief look at all the physical aspects of the silicon solar cells. I hope you had a good time, and I hope to see you soon.